Hello everyone, I'm Tiefu Zhao. I'm assistant professor at the Department of Electrical and Computer Engineering at UNC Charlotte. On behalf of all the team members shown on this slide, I'd like to present our project, Modular Hybrid Silicon Carbide and Silicon-Based Battery Inverter for Energy Storage Integration. I also want to use this opportunity to thank Power America for continued support of our research. Our team includes UNC Charlotte and LS Energy Solutions. Both are located in Charlotte, North Carolina. At UNC Charlotte, we have been conducting research in wide bandgap device-based power electronics, such as this project, the hybrid silicon and silicon carbide switch-based battery inverter, and also the medium voltage solid-state circuit breakers. The picture on the right-hand side shows EPIC's Flexible Energy Laboratory, which is a lab to conduct high-power testing of power converters up to 1 megawatts. Our industry partner is LS Energy Solution, formerly known as Parker Hannifin's Energy Grid-Tied Division. LS Energy Solution is a leader in energy storage industry, and they have a proven track record with over 450 megawatts of energy storage system installed. So the goal of this research partnership is to advance the technology from the concept level to the system level toward commercial viable silicon carbide inverter. Our technical project objective is to develop, test, and demonstrate a 50 kilowatts, 1500 volts DC hybrid silicon carbide and silicon-based inverter for energy storage integration. This proposed solution is an active neutral point clamped A-NPC inverter based on optimized unipolar device in parallel with bipolar device. And our approach basically combines the advantages of the two types of devices and introduces silicon carbide benefits to the 1500 volts battery inverter at a significantly lower cost compared to the state-of-art pure silicon carbide inverter technology. At the same time, this solution offers a way to provide high efficiency and high power density to the energy storage integration. Our performance target is to achieve 99% CEC efficiency and 45 watts per cubic inch high power density with reduced LCOE. So based on the progress we have achieved so far, we believe that we are on the right track of achieving this target at the end of this project. At the same time, we will work with LS Energy Solutions to use their new product development process and develop a commercialization plan for this hybrid silicon and silicon carbide technology. On the education side, so far we have 2 excellent graduate students and 2 undergrad students involved in this project. And the work I'm presenting here is mostly their contributions. Our technical solution is based on the proposed hybrid silicon carbide and silicon switch as shown in the figure here. This is a fundamental component that will enable the combined benefits of silicon carbide unipolar device and silicon bipolar device. Particularly in our project, we are developing a hybrid switch consisting of 1200 volts silicon IGBT and 1200 volts silicon carbide MOSFET. If you look at this IV curve of silicon IGBT, silicon carbide MOSFET, and the proposed hybrid silicon and silicon carbide switch with similar current readings, the hybrid switch has lower conduction loss than silicon IGBT at light load region, and also lower conduction loss than the silicon carbide MOSFET at heavy load region. So our project first investigates the optimal design, such as optimizing the die size and current ratio between the silicon carbide MOSFET and silicon IGBT. The right-hand side figure shows the optimization flowchart. This optimization process ensures that we're going to use just enough silicon carbide device, but still maintain the high efficiency and safe operation of both silicon and silicon carbide devices. For example, in our 50 kilowatts, 1500 volts 3-level inverter application. We have selected a 15 amps IGBT and a 12.5 amps silicon carbide MOSFET to form the hybrid switch. Right now, we're only using discrete devices in this project, but the same optimization process for die size optimization can also be done in the die level to make a hybrid switch module in the future. The proposed hybrid switch here takes advantage of more than just an efficient conduction path. Because the silicon carbide MOSFET typically has a faster switching speed than the silicon IGBT, a dynamic gate driver and switching pattern for this hybrid structure is needed to balance the different switching properties of the two devices. The commutation of the hybrid devices are also considered differently with regard to the variation of load current. For example, as shown in this figure here, the load current is divided into 4 regions based on the current magnitude. For example, in region 1, only silicon carbide MOSFET is conducting. In region 2, both devices are conducting. The silicon carbide MOSFET is turned on first and turned off last to achieve 0 voltage switching for silicon IGBT. In region 3, silicon IGBT is turned on first and turned off last to provide the inverter overload capability. In each current region, the switching pattern is developed to minimize the hybrid switch loss and also ensure the safe operations of both silicon carbide and silicon device. The developed silicon and silicon carbide hybrid switch was tested in the pulse tester to study the switching characteristics. The top 2 waveforms show the turn on and turn off process of the hybrid switch. And you can see that the MOSFET is turned on first and turned off last. And also from the waveform, you can see with the proper delay time between the 2 gate signals, the 0 voltage switching of silicon IGBT can be achieved. The bottom 2 figures here illustrate the turn on and turn off energy comparisons between the hybrid switch and the silicon IGBT in the same testing condition. And the red curve is the hybrid switch E on and E off at different currents. The black curve is the E on and E off for silicon IGBT. And you can see from the comparison, the hybrid switch shows significant reduction in both turn on and turn off energy compared to the silicon IGBT counterparts. And here's the proposed silicon and silicon carbide hybrid switch-based A-NPC inverter for 1500 volts DC application. And we have evaluated different hybrid methods in the A-NPC topology. So by considering inverter efficiency, thermal performance, and cost trade-off, we decided to only replace 2 switches out of the 6 switches in each phase lag shown here with the hybrid switches. So with the improved PWM modulation method shown here, only the 2 hybrid switches are switching at high frequency, the switching frequency. All the other switches are switching at twice of the line frequency. So in this way, we were able to reduce the number of hybrid devices in this A-NPC topology, but also maintain a very high CEC efficiency as shown in the efficiency curve. We have also optimized the inverter thermal and package design to achieve a high power density. So the major challenge in our design here is the heatsink and the capacitor size. So we were able to reduce the required capacitance through control method. We also placed the hybrid switch power board on an individual heatsink to avoid sharing a bulky heatsink with a half-bridge IGBT module. And we also have a design pluggable gate driver board, which helps to reduce the overall system volume. And so far, the estimated efficiency is above 99%, and the power density is around 45 watts per cubic inch, which is 3 times of the current product density here. And to summarize our accomplishments in the past year, we have completed the hybrid switch-based A-NPC inverter design. So in our research, we have proposed a silicon carbide and silicon device optimization method, a dynamic gate driving and switching pattern to achieve the high efficiency target. We also evaluated different hybrid methods for A-NPC inverter topology and developed a compact inverter package to reduce the size and increase the power density. And we believe that we're going to achieve that 99% CC efficiency target and also the 45 watts per cubic inch power density for this 50 kilowatts and 1500 volts battery inverter. Our future work includes conducting full power testing and demonstration of this hybrid switch-based A-NPC inverter in UNC Charlotte EPIC Lab, and also validate the performance metrics through experiment. And this concludes my presentation. Thank you for your attention. Please let me know if you have any questions or comments, and enjoy the rest of the workshop.